Only the second energy project we've had here. Our energy track is a very, very new track, and so I'm really excited to present to you the ME435 Energy Engineering Preliminary Design class. The design team lead is Dana Felber, and she's going to introduce her team and tell you a little bit about their project.
All about our thing.
Yeah. Thank you very much.
Thank you for that introduction, Dr. Heyman. So as she stated, we are AEOS Enterprises, a mechanical engineering preliminary design team working on an alternative energy project. So this is our final preliminary design presentation. Again, my name is Dana Felber, and I will start with the project introduction of the solar thermal rig we are designing. Before going into the details of our design, I would like to introduce my team. Yet again, I'm Dana Felber. I'm the design team lead. We have Cheyenne Baltonato, Brian Bishop, Natalie Chackers, Stephanie Frederick, and Richard Garcia. So throughout the duration of this semester and next semester, our team is designing, building, instrumenting, and testing a solar thermal power generating rig. The requirements for our system, as designated by our request for proposal, or RFP, are as follows. Firstly, our rig must be approximately desktop sized. It will operate on a cycle and produce a minimum net power output of 100 watts. Our rig will be instrumented in 3 distinct locations to determine temperature and 1 location to determine pressure. We will also must use an environmentally stable working fluid. In the context of our project, environmentally stable means non-flammable, non-toxic, and non-corrosive. Our final requirement is that we must stay within a budget of $1,000. So you might be wondering, why is this important? Because in our society, 100 watts is not a lot of power. But with 1.2 billion people worldwide lacking access to electricity in 2014, there's a critical need for small-scale alternative energy power systems. In order to make electricity accessible to all, we need a worldwide diversified profile of energy systems, because large-scale grid power like we have in the United States is not feasible for every community. I'm not saying that our project will end energy poverty, but rather that there is an indisputable need for research and development into small-scale, single-unit power generation, much like what our team is designing. This is a very simplified schematic of our system. We are using a Fresnel lens to concentrate solar energy onto the hot piston of a Stirling engine. Using a cycle of heating and cooling, our Stirling engine will spin a flywheel. This flywheel will interface with an electrical generator via a pulley. This electrical generator will convert our mechanical work to electrical work. As stated, we are hoping to get 100 watts out of the electrical generator. Assuming a generator efficiency of 90%, this means we will need 111.1 watts into our electrical generator. Assuming a conservative Stirling engine efficiency of 27.5%, in order to get our 111 watt output of the Stirling engine, we need approximately 400 watts into the Stirling engine. Assuming another conservative Fresnel efficiency of 70%, this means that we need a minimum Q in from the sun to the Fresnel lens of 600 watts. So now we will discuss the component design of our project, starting with the solar collection given by Natalie Chackers.
Thank you, Dana. Again, my name is Natalie Chackers. I am the solar team lead for AEOS Enterprises, and I will be going over solar collection. To begin, I'd like to start off by telling you about some design considerations we had to take into account before looking at different types of collectors that we will use for our solar thermal rig. First off, this is a solar thermal rig, so we need to utilize solar energy. Second, as Dana stated in the previous slide, we need 600 watts minimum coming into the solar system, or the solar collector, to create a net output of 100 watts going out of our system. And third, we need a collector of at least 1 meter squared, because on average, 1,000 watts per meter squared comes to the surface every day here on Earth. 1 and 2, the team looked at 3 different types of collectors that fit our design considerations. First off is the parabolic dish, second is the Fresnel lens, and third is the parabolic trough. Here is our criteria matrix. We weighed efficiency and cost as our highest weighing factors, and after applying all the weighing factors, we found that the Fresnel lens was our best choice. After deciding on the Fresnel lens, we needed to learn how the Fresnel lens works. As you see here on your right, there's a picture of the Fresnel lens. It is perpendicular to the light source that is being used. The light comes into the Fresnel lens on the rich side of the lens. It is focused to a single point called the focal point. At this focal point, we will position our hot cylinder head at a calculated focal length. Here, the energy will be concentrated onto that head and be used to power the rest of our system. After applying our first Fresnel lens, the team went into preliminary design testing. We used sample items such as water and a steel sample that much like that would be used in our heater head. The water testing that we did was to see how much time it would take to get a rolling boil out of our water. The steel sample testing that we did was positioning the collector at different times of the day. We wanted to see what temperature we could get on the steel samples. Due to cold weather and windy temperatures, we concluded that our tests were unsuccessful. The heat leaving the system was a lot greater than that was entering the system. So after finding out that we were unsuccessful, we did some more research and found that there are 2 different types of Fresnel lenses. On your left-hand side, you can see the spot Fresnel lens, which is the one that we need to acquire for our solar thermal rig. On the right-hand side is the linear Fresnel lens, which we did preliminary testing with. On the 2 right-hand pictures, you can see the focal points, and I'd like to highlight these 2 pictures. On the spot Fresnel lens, you can see a very distinct image of a clear and bright focal point. This is a high-intensity powered lens. Whereas the linear Fresnel lens, on your right-hand side, this is a picture of the actual focal point taken from the Fresnel lens testing that we did. As you can see, the light is very scattered and very dim, giving us a low-intensity lens. Going into phase 4, the team decided to redo our criteria matrix. Instead of the Fresnel lens, or the linear Fresnel lens, we put in place the spot Fresnel lens and didn't change anything else. After using all the weighing factors again, we found that the Fresnel lens is still the best choice for our solar thermal rig. So going into detail, we will acquire a spot Fresnel lens, and I'd like to talk about some disadvantages and some advantages to the Fresnel lens we will be using. The spot Fresnel lens is able to focus light up to a 500-to-1 ratio. The spot Fresnel lens that we will be acquiring is actually rated to reach temperatures of 1100 degrees Celsius and has an efficiency of about 90%. Some disadvantages that we found that come with all types of Fresnel lenses is that if the light source is not perpendicular and direct with the sunlight, you're not able to get optimal solutions. In order to counter this, the team will be calculating an incidence angle at all positions at all given times for testing during our detailed testing. And then the third thing that we found out about this, all types of Fresnel lenses is that any surface imperfections, such as dents or scratches, can greatly degrade the performance of our lens. In order to counter this, a simple cover will be placed on the lens at any time that there is no testing. So going into detail, we need some predicted Q-in values to we need some predicted Q-in values to compare to the tested values that we get when doing testing in detail. So the calculation for Q in at a collector uses many variables, which we have broken down into 3 different types of categories. First being the atmospheric and solar categories, second being position and time, and third being constants and coefficients. Going into a predicted value of what we can get during our testing them in detail, position and time are very important to the calculation for incidence angle. The position being here, where we will be doing our testing, and we also use a time of date being February 1st, around when we predict to start testing. After doing that calculation, we get an incidence angle of about 12 degrees. Going into the second part of the calculation, we need to utilize the atmospheric and solar values along with constants and coefficients, such as the ones seen on the screen. And from about 1 p.m. to 2 p.m., we can expect about 900 watts to come into the collector, which is greater than the 600 watts predicted, needed to give a net output of 100 watts. And next, Ryan will talk about the Stirling Engine.
Thank you. My name is Ryan. I'll be speaking about our Stirling Engine. The Stirling Engine is a hot air engine that operates by expanding and contracting a fixed mass of working fluid within its cylinders. The working fluid for our Stirling Engine will be air. The heat is added external to the cylinders, and therefore the engine is considered to be an external combustion engine. There are 4 strokes per cycle, and in the case of a Stirling engine, 1 rotation of the crankshaft. Those are expansion, hot transfer, contraction, and cold transfer. This is to help you visualize the layout of our Stirling engine. On the left is our hot cylinder, which the heater will be affixed. On the right is the cold cylinder, which the cooler will be affixed. And in between is the transfer passage containing the regenerator. During the first 90 degrees of crankshaft rotation, the working fluid is expanded by the external heat source, causing the pistons to be forced down in their bore. The kinetic energy stored in the flywheel carries the crankshaft through its next 90 degrees of rotation, where the working fluid is transferred from the hot cylinder through the regenerator, where a portion of the heat energy is stored, and on into the cool cylinder. Once the majority of the working fluid is in the cold cylinder, it begins to cool and therefore contract, drawing the pistons up in their bore. Again, the kinetic energy stored in the flywheel causes the next 90 degrees of crankshaft rotation, where the cooled working fluid is transferred from the cold cylinder through the regenerator, where it recuperates some of the stored energy, and back into the hot cylinder to begin the cycle anew. On the left, you can see the air compressor pump that we purchased and will be modifying into our Stirling engine. It is a 3 horsepower, 90 degree offset V-twin piston engine. On the right, you can see the CAD model of our engine block with the designed cooler, heater, and flywheels attached. Next, we have Richard speaking about our heater design.
Yes, thank you, Ryan. The heater design is part of the Stirling engine, so I'm talking about that today. First, we need some design consideration for the heater head. First, in the engine to effectively receive and transfer heat to the heat single chamber. It needs to maximize the wet area inside the central chamber, also minimizing the water volume inside the central chamber, and minimizing the vector losses, and also be instrumental for instrumentation. Next here we have 5 materials that we decided to make the heater head from. And all these materials have thermal coefficient that we need for the heater head. But stainless steel at the bottom has the highest temperature of all of them, and must be fixed around a little less than this in degrees. So you don't want our material to melt. So we chose stainless steel. Next, here's a quick draft and drawing we did at CATIA. And the overall dimensions of the heater head are 4.75 inches squared in diameter. And the thickness of the heater head is 1 inch squared. 1 inch, sorry. And here's the actual CATIA model that we created in CATIA. Now again, the diameter is 4.75 inches and thickness is 1 inch. Here you see 3 ports. The transfer port, the CSG port, which is the center heat temperature port, and the pressure port. And in the middle, you see a hemispherical sphere for the piston. Here is the temperature solution that we did one analysis as we input the part into the analysis. Here you see a temperature of 1,150 degrees above in the top of the cylinder head, and now you see about 990 degrees Celsius in the bottom of the cylinder head. We need about 1,000, so 10 degrees less than that is perfectly okay for now. So this tells us the model that we actually decided on is pretty efficient. Next is we saw a flaw in our control model due to an analysis. First, this port is called the CHT port. You can stick a sensor in there and record temperatures. But this temperature won't be able to read all the temperatures that it's facing at the bottom of the cylinder. And so we had to make this a little deeper. On the right side of the picture, you see the bottom of the hole is a dark blue shade, which means this reading the maximum, most of the temperature. So that's probably fixed by making the hole a little deeper. Not all the way through the wall, but just a little deeper. Next is Ryan Bishwian with Cornelis.
Thank you. Again, I'll be speaking on the cooler. The cooler is affixed to the cold cylinder of our Stirling engine. The purpose of the cooler is to effectively reject the heat in the cold cylinder. To do so, it's desirable to fabricate the cooler out of a material with a high thermal conductivity. The cylinder chamber should maximize wetted area while minimizing void volume. The wetted area is the effective surface area in which the working fluid is in contact with, and the void volume is the space within the cylinder that is not swept by the piston. It is also desirable to maximize the effectiveness of the cooling fin and to make sure that the head is fit for instrumentation. As mentioned, the material used to fabricate the head should have a high thermal conductivity. You can see here that copper and silver have a high thermal conductivity, but will not withstand the temperatures and pressures that we expect to experience within the engine. Although ferrous metals have an acceptable durability, you can see that their thermal conductivity is relatively low. This led us to choose aluminum, specifically a 5-inch round 6061 aluminum billet in which to fabricate our cooler from. Here you can see the general dimensions of our final cooler drawing or design. Again, it has a 5-inch diameter. It will stand 2 inches tall with 11 1-inch tall, 1/8 inch thick cooling fins and annular fins surrounding the radius. The cooler will feature a hemispherical chamber that maximizes the wetted area while minimizing void volume. There are 3 ports: the pressure port, transfer port, and cylinder head temperature or CHT port. The pressure and transfer port extend into the cylinder, however, into the chamber. However, the CHT port does not. As mentioned previously, there are 11 straight rectangular fins on the top surface and 3 annular fins surrounding the radius. Once we completed our CAD model and initial thermal cycle analysis, we were able to upload our model into ANSYS to perform a steady state thermal analysis. Here you can see that our cooling fins are perpendicular to the heat pattern seen at the base of the head, and that there are 4 extraneous fins seen in dark blue adjacent to the cylinder head bolt holes. This model showed us a temperature difference between the base and the fin tip to be 22 degrees. We removed the extraneous fins adjacent to the cylinder head bolt holes and rotated the remaining fins 90 degrees to match the heat flow, or the heat pattern on the head. This brought our temperature difference from the base to the fin tip from 22 degrees up to 26 degrees. Next, we optimized the thickness of the fin, reducing it from 3/16 of an inch down to 1/8 of an inch. This brought our temperature difference up to 31 degrees, and as you can see, the area in red at the base of the fins is now at the same temperature ascribed to the cylinder chamber. The next dimension optimized was the fin height. Although it would be advantageous to have an infinitely long cooling fin, this is not feasible. Therefore, we constrained the maximum height of the fin to 1 inch in hopes to prevent damage during handling and fabrication of the head. As you can see here, this brought our temperature difference up to 40 degrees. It should be mentioned that this temperature difference is what drives convective heat flow. As Richard mentioned, with the heater, we did find a flaw in our original design. The temperature at the bottom of the CHT port was not at the same temperature ascribed to the inner chamber surface. Again, we increased the depth of this hole until it maintained the same temperature that is described in the chamber surface. Next, we performed a wall thickness analysis using CATIA. This shows that the cylinder chamber wall near the CHT port is just under 60 thousandths thick, which will be sufficient to withstand the pressures and temperatures we expect to see in our cylinder. Next, Cheyenne will be speaking about our regenerator design.
So as Ryan mentioned, I will be speaking about the regenerator design. To recap, the regenerator is located between the hot and cold cylinder within the Stirling engine. So first, we want our Stirling engine to have as high of an efficiency as possible, as close to the Carnot or ideal efficiency. The regenerator is one component that can help and aid to that. As seen in the photograph, that is where the regenerator is located. The intent of this component is to remove as much heat as possible from the air that is exiting the expansion cylinder. While the air moves through the regenerator matrix, the matrix will remove and store heat prior to entering the cooler on the top of the cold cylinder. This will reduce the energy requirements for the cooler. The same process will occur on the return as the air moves from the cold cylinder to the heater. This regenerative process gives Stirling engines higher efficiencies. For the regenerator, we would like to maximize the surface area while minimizing the dead volume within the engine. There are two components that make up the regenerator: the exterior pipe and the interior matrix. When looking at previously made Stirling engines and their publications, we found that the two most commonly used materials were copper and steel. Copper was more widely used because of its thermal conductivity, and with that, its ability to absorb and release heat. The downside of copper is that it does deform with heat. In relevance to our system, the deformation can cause expansion within the pipe. That expansion with additional cooling later when the engine is not operational can lead to leakage of the air from the system. For that reason, along with the fact that the previously mentioned max temperature can reach up to 1160 degrees Celsius, which is above the melting point of copper, steel was chosen for both the pipe exterior and the interior of the generator. When discussing the interior of the regenerator matrix, there are a few different options the team could select from. These are listed in the PowerPoint along with the graphic to show what they are. The most commonly used in the Stirling engine publications are the mesh and foil types. The mesh types in practice and in performance have shown to fall apart during operation due to turbulent flows and high temperatures. With the breakage of the mesh, it can enter the cylinders, which are not ideal for performance. For efficiency and simplicity, the team has decided to go with the foil design. When preparing our bill of materials and costing out the foil for our system, we found that the smallest amount of foil that can be purchased is enough for us to create two different configurations. The two different configurations first would consist of a conventional foil type, a conventional foil coil type, which would be similar to taking a sheet of paper and rolling it into a cylinder. This also helps to insulate the interior of the pipe. The second option would be a dimpled coil foil. This would be similar to a helical coil shape with the interior dimpled by a seamstress wheel. For the final regenerator design, when the team is testing in detail, we have the option of expanding our regenerator length from 5 inches to 8 inches if we see fit that the regenerator length will increase the performance of the engine. As previously mentioned, there are two types of matrix types that we can utilize. This will give us the option of utilizing 4 different configurations of regenerators for the system. When analyzing our Stirling engine, we will be using a MATLAB code, which will be discussed shortly by Ryan. The most pertinent variables in relation to the regenerator are the inner and outer diameters of the pipe. The inner diameter of our pipe that we have selected is 1/2 inch. The length of the regenerator, the matrix type, which is again the foil, and the foil thickness. Next, Ryan will talk about the Stirling engine analysis.
Thank you. We were fortunate enough to come across a wealth of information from Ohio University's Stirling Cycle Machine Analysis course and Professor Israel Areli. The course provided us with more than 50 pages of MATLAB code and function that allow us to perform adiabatic, isentropic, and simple Stirling cycle analysis. The code was adapted to better represent and describe the current geometries within our system. This is an example of the code inputs and a few iterations that we have performed. As you can see, there are many inputs, but they have been organized into 5 main categories, where the heater, cooler, and regenerator are our design points. Once running an iteration of the code, there are many useful graphical outputs. Here you see a pressure volume diagram. This shows our maximum and minimum pressures. These values will be used to further refine our predicted maximum power output using the West number that will be described shortly. These values will also be compared to the values taken by our instrumentation during testing. Another graphical output is our maximum temperatures seen within one cycle of the engine. This shows the maximum temperature of the heater, the cooler, and the effective regenerator temperature. Again, these values will be used to further refine our power output predictions and to compare to measured values within testing. Our current iterations indicate an ideal thermal efficiency of approximately 55%, with a little less than 1,000 watts of energy being transferred to the hot cylinder, a little less than 500 watts being transferred from the cold cylinder to produce a network output of approximately 600 watts. Due to the quality and level of technology used to fabricate the air compressor that we purchased and will be modifying, and installation losses, whether at the solar collector, convective losses at the head, or drag losses within the engine, we expect to see values approximately half of the ideal values. This is a graph that shows the power output as it relates to engine frequency, or RPM. The predicted red line for our engine is approximately 1,200 RPM. Using the West number, this outputs a maximum expected work of approximately 150 watts. This is an ambitious value, but it does outline the maximum that we could expect. The West number is derived from empirical data discovered during testing of many Stirling engines across the last 5 decades. It is a function of the mean pressure, swept volume, frequency of the engine, and does include a temperature correction. Next, Dana will be speaking of our flywheel design.
So the final design aspect of our Stirling engine is the flywheel. The flywheel is important for 2 main reasons. First, the flywheel stores energy generated by the power stroke, then converts that energy back to the crankshaft when the pistons are at their full extension. This energy transfer prevents locking up of the pistons and ensures that the engine remains in continuous rotation. The flywheel is also important because it interfaces the Stirling engine with our electrical generator. This interfacing is done via a pulley system. When designing our flywheel, the first design choice we made was the material selection. The team decided to manufacture the flywheel out of steel. This decision was made from a budget consideration. We are purchasing a steel billet to manufacture our heater head, but we do not need the entire length of the billet for the head. Therefore, we will be using the remaining material to manufacture our flywheel. This design choice constrained our flywheel diameter to the diameter of the heater head, which is 4 3/4 inches. An important design consideration when designing a flywheel is that the kinetic energy of the flywheel upon startup of the engine must be sufficient to overcome the static friction of the flywheel, the crankshaft at rest. Through experimental data, we calculated that a required torque of 0.25 Newton meters is required to start turning the crankshaft in the flywheel from rest on the compressor pump that we purchased. We chose a flywheel design with a kinetic energy of 0.287 Newton meters. This kinetic energy was calculated upon using the startup velocity of the engine, which is approximately 100 RPM. This is a diagram of the flywheel dimensions. As stated before, the outer diameter is 4 3/4 inches. It is also approximately 2.17 inches thick. That thickness is both the flywheel and the collar. One other notable dimension is the internal diameter of the collar. This is approximately 1.18 inches, and this is the same as the diameter of the crankshaft. So the crankshaft and the collar will fit flush together. Now we will move from the Stirling engine onto the electrical generator, where Cheyenne will discuss the power generation.
So as Dana mentioned, I will be speaking about the power generation for our system. When looking at this, we're looking at taking our mechanical power that we've been discussing and turning that into electrical power. As mentioned in the beginning of our presentation, we're looking for a net power output of 100 watts. For these purposes, we have two different testing methods that we can use. The first method will utilize an AC generator. The second method will utilize a DC generator. The first method is a little bit more simplistic, and the second method would require some configuration. When looking at a generator that would fit the needs of our system, we needed a generator that would not inhibit the engine as it was moving to its operational speed. For these reasons, the team looked into a wind generator. The wind generator is shown as pictured in the yellow circle and in its typical application with a wind turbine. For the first method, with an AC generator, there was a lot of information and specifications supplied should we purchase this generator. A summary of that information is shown in the table below the graphic. Our testing process would start with an initial spin of our flywheel to get the engine moving. If we are recording a speed of approximately 860 RPM consistently at the shaft of the generator, we can then verify that our net power output would be 100 watts. For the second method with a DC generator, there's a little bit less information and specifications provided with this generator should we purchase it. This would require a configuration process. The configuration process would consist of us using a drill at the shaft to spin the shaft of the generator. During that time, we would use multimeters to measure the voltage and the current. The product of the voltage and the current will give us the power in watts that we are looking for. We can also use a tachometer to measure the speed of the shaft as it is spinning. We would use all of these things and test the generator to find the operational min and max points in relation to our engine. The testing process would be similar, and we would start the engine with a simple spin of the flywheel, and when we are measuring the correct product of voltage and current, we would get our net power output of 100 watts. What that would mean is that if we were measuring 12 volts, we would need approximately 8.4 amps to get 100 watts. Next, Stephanie will talk about instrumentation and data acquisition.
Thank you, Jan. Our RFP states that we need to measure both temperature and pressure. In addition to measuring temperature, the ambient and room temperature, we will also be measuring temperature at 3 locations within our rig. The temperature of the hot and cold cylinders, as well as the temperature in the generator. It's important to know the temperature of the hot and cold cylinders, because with this we can make calculations such as getting the efficiency and the power out, as well as being able to compare our actual results with our theoretical calculations. There are 2 common ways to measure temperature, a thermocouple and a resistance temperature detector, or RTD. We decided to use a thermocouple because while RTDs are more accurate, they're also more expensive. The accuracy of a thermocouple is about plus or minus 1 degree Celsius, which is adequate for our requirements. RTDs are also used for lower temperature applications, up to about 500 degrees Celsius, and our expected temperatures are more than twice this. For these reasons, we've decided to use a K-type thermocouple because of its wide temperature range and its ability to handle high temperatures. As you can see, our maximum expected temperature is within the range of our thermocouple. In order to attach our thermocouple to our rig, we're using an NVT type threaded connection, such as the one pictured here. This will enable us to have consistent and accurate readings. Once we knew that we were using a thermocouple, we performed a test to gain hands-on experience with a thermocouple and the LabVIEW software. A basic test was set up to measure the temperature of water at 3 different temperatures: at room temperature, at boiling, and close to freezing. These were chosen for their known values and relative ease to produce. The premise being that if you measure known values, we'll know what numbers to expect and know if our thermocouple in our code is working. At first, we put one end of the thermocouple in water and put the other end of the thermocouple was attached to the computer and the LabVIEW software via a motherboard. The LabVIEW software takes the voltage input from the thermocouple as well as other inputs such as the type of the thermocouple. We're using a type K as well as a type E for comparison. Also the location, which port in the computer the thermocouple is plugged into, and other inputs such as units. The software takes all of this information and converts it to a temperature. Timestamped data is then stored and exported to Excel where it can be graphed. This is the graph of our results in degrees Celsius versus time. Roughly the first minute of the test was used to establish a baseline, And then one thermocouple was placed in the ice water, and the temperature got down to about 6 degrees Celsius. The next thermocouple was placed in the room temperature water, and the temperature stayed roughly constant. The last thermocouple was placed in the boiling water, and you can see the temperature got up to about 98 degrees Celsius. These were the temperatures that we expected, so achieving our expected results means that our thermocouples, and more importantly, our code is working correctly. The error that you see in the red circle was because the thermocouple came out of the water during testing and then was put back in, but this won't be a problem during our rig because of the NPT type connection that I mentioned earlier. We also need to measure pressure. The pressure in the hot cylinder should be about the same as the pressure in the cold cylinder. So we're going to be measuring the pressure in the cold cylinder so that the high temperatures in the hot cylinder don't damage our instrument. We'll be using a compression tester similar to the one used in the automotive industry, with also the same NPT type threaded connection. Our pressure reading will be able to be read manually off the base of the gauge. And now Dana will tell you about our conclusions.
So now that we have discussed each aspect of our design, this is a representative diagram, or excuse me, drawing of how everything will look in the completed rig. So all the dimensions on this drawing are to scale. The Fresnel lens is 65 inch, and it will be mounted on a frame that can tilt, so we can position the Fresnel lens based on the position of the sun in the sky. Resting on the tabletop is our Stirling engine and electrical generator. On the left side is the heat head, where facing the Fresnel lens, and then on the right side is the cool piston. Then sitting next to the engine is our electrical generator connected with a pulley. To summarize, our key design features are: we are using a Fresnel lens to concentrate solar energy. We are designing custom heater and coolers to fit on the piston heads to effectively transfer heat from the Stirling engine. We're using a custom regenerator to increase the efficiency of our Stirling engine, and we are using a small electric generator to interface the engine we are using a small electric generator to create our power output. So as discussed by Natalie, we expect approximately 900 watts into the Fresnel lens from the sun. Assuming a 80% Fresnel lens efficiency, this means we should be getting approximately 720 watts out of the Fresnel lens onto the Stirling engine. Assuming a conservative Stirling engine efficiency of 20%, this accounts for losses such as friction losses and convective losses of the heater head. We are expecting approximately 144 watts out of the Stirling engine. Assuming a 90% electrical generator efficiency, we are expecting approximately 130 watts out of our system. As mentioned before, our budget for our project is $1,000. We have currently spent approximately $96. Most of this went to purchasing the compressor pump that we will be modifying into our Stirling engine. Based on our bill of materials, we are expecting a total expenditure of approximately $780, leaving approximately $220 left over for any unanticipated expenses that we might encounter during detail. Our preliminary plans for detailed design are outlined in the following flowchart. At the beginning of the semester, we will start with solar testing and electrical generator testing. We will also begin component fabrication. Once we have fabricated the heater, cooler, regenerator, and flywheel, we will do testing on each of the individual components. Once we are satisfied with our components, we will do a complete engine assembly with instrumentation. We will then integrate, and we will then perform engine testing. We will integrate the solar, engine, and generator components of our system to create our complete rig. We will spend the remaining time in this semester doing iterations of rig testing and design optimization so that we can get the most power output as possible. This is our graph of our man hours worked throughout the course of the semester. We did work approximately 160 hours more than our projected hours. Finally, I would like to conclude this presentation by thanking some of the Embry-Riddle faculty and staff that have really helped us throughout the course of this semester. Drs. Haven, Haslam, Fabian, and Danley, as well as Professors Zwick and Helbling, and Mr. Clauser. Thank you for your time and attention. I know this was a late presentation, but I really appreciate it. We really appreciate everyone being here. I will now open the floor to questions.
Nice presentation. Very good. 59. Go to 59. Okay, does that generator, is it happy at 129.6 watts that you guys are playing with? Or does it cut out, or do you know? Or is that just, is that an example and you're still doing more work?
Cheyenne is the most familiar with the specifications of the generator, so she can answer that question.
So the rated power in watts is 100 watts. The max power that they show for the rating for this AC generator is around 150 watts. The same configuration process can be applied to this AC generator if you did want to find the min and max points, as the specifications are just general values and not always as accurate as we need.
Okay, all right. Okay, so I wanted to connect the dots because you finished at a much bigger number. Are you playing games with clearance volume, Mr. Machinist? For your hot and cold side?
In what dimension?
Well, at all. You said you wanted to eliminate your voids at the top for the non-swept parts.
Yes.
So you're a hot rod motorcycle guy, so I'm figuring you're gonna play with this thing and try and get the sweet spot.
Yeah. So we have in the appendice the part of the mass plots. Yeah, it would be one of the last few in the appendice. Currently, both chambers are of the same dimensions. Obviously, you're limited by the 65 millimeter bore of the piston,
Right.
but you can adjust both the height value, which is from the deck of the cylinder head to the top of the cylinder chamber, and then also the overall radius of the sphere that you use to create the pocket. Not this one.
Yeah, it's not this. We
Oh,
don't have it.
we don't have it.
So
Okay.
are you using their software that you found?
Yes, we're using the MATLAB code there is. You don't, unfortunately, don't have this graph up there, but it shows the reduced or specific volume within the engine during the entire cycle. And it actually indicates that although we have similar geometries for both the heater and the cooler void volume could actually be reduced and it would be beneficial. Just kind of playing around with those numbers, it output more power, but it actually reduced our thermal efficiency.
Okay. All right. How do you guys start it? You got a lawnmower pole, or is it less than that?
Our plan is just to heat up the cylinder for a little while and then just hand spin it.
And spin it,
And
it
then-
should be that soft. All right. Do you have to prime it with any extra air? Some of the systems, you actually put extra air into the cylinder above and beyond, above atmospheric. Some of the schemes have that. Do you guys have to do that, or are you using atmospheric?
Current plans are to start with atmospheric air. You have an oil fill passage or oil fill port and a breather port on the engine. Using those, we can do pretty much a dump valve setup on one side to regulate the output, and then input either air or another working fluid if we are successful, such as helium.
Right.
Pressure within the crankcase, which is also relative to the static pressure within the cylinders. That is linearly related to power output. So the more we pressurize that case, as long as it stays within the seals, we make more power.
Okay. Those are my B's. Nice job.
Got a couple questions. I was wondering about the absorber design. Is it just bare metal or?
Absorber as the heater?
Yeah,
Yeah, it's just stainless steel. It'll be affixed to the top of the cylinder head. We haven't gone far enough through our analysis to say that the overall external shape will reduce convective losses, but it is in the books to possibly look into insulating the areas of the head that are not in direct contact with the focal point, or the focal point of the solar collection.
Okay. Did you consider coating it with the low emissivity coating?
We didn't, but we will be.
I was wondering on the MATLAB numbers, there's 1,000 watts mentioned. How does that fit into the other numbers?
You might have to pull up that
Do you
slide.
have a
Just
slide
so-
number?
Yeah, we have a slide number, 50.
Yeah, 50.
Oh, the heat transfer to the hot cylinder?
Yeah.
Is that the number you're looking at? Okay, so we're currently our lens is 1.2 square meters. So we could expect, maximum, let's say 1,200 watts going into the lens, and then you kind of dumb that down through losses at the head. This number comes from the cycle analysis just based off the temperature ascribed by the lens. So it has nothing to do with actual energy input. It's just a number that comes out at the end, which is in line with what we could expect to be at least transferred to the top of the cylinder head, maybe not through the cylinder head into the chambers, but at the top surface of the cylinder head.
Another simple question, did you have a frame for the Fresnel lens?
I will-
Or Fresnel lens, sorry.
Yes, so we obtained a Fresnel lens from a back projecting TV. So we took the TV apart and took the lens out.
With the frame?
So then we built a frame for our lens out of wood. And although the lens that we have currently will not work for our system, the lens that we are looking into purchasing comes with a frame.
Oh, that sounds good. Very good job.
The only question I have, and I think you covered this, but I think I actually missed it, and again, it's a late presentation, so I apologize. When you were discussing the design of the interior of your regenerator, you mentioned there were a couple of different options, and I was hoping you could go into a little bit of detail on the selection process.
Is there a slide number that I
That
can go
was
to?
slide 43.
Okay, so for these options listed match the figure that is next to it. This came from a NASA publication for Stirling Engines, and this is the different options that they've discussed. The reason that I didn't touch too much in depth on any of the other options is because for the purpose of listing all the options available, this is why I showed this. But for Stirling engines that were used on Earth and not in any kind of other applications, the most widely used were just the mesh and foil options. So if you Google like how to make a Stirling engine, the options that you'll find were the mesh and the foil options. No one really uses the ball options. The composite options, I'm not quite sure how that works, but that hasn't been shown. Like the results of the regenerator matrix being in that configuration aren't shown or published anywhere that we could find.
What was then the selection process for going between either the mesh or the foil?
So the decision process between the mesh and the foil was really simple. We just sat down as a group and determined that the foil option would be better because in performance evaluations of previously built Stirling engines, the mesh has shown to fall apart and then enter the different cylinders of the engines. And because there is turbulent flow within the regenerator passage and then fluctuating temperatures, there's a really good chance that this falling apart of the mesh can happen. The mesh material is again stainless steel. So with that in mind, we decided to just go for the simplest option, which is the foil.
Okay.
Anybody?
So you seem to have a pretty big lens and a desk to actually hold this engine. So you're using solar energy. Why not just use a solar panel where you could get? Well, what is the advantages of using this over something much simpler, such as like a solar panel, where you could have multiple and produce, equal or more, the energy?
So the word solar panel to me is very broad. So there's a solar panel, there's a photovoltaic system. So that's a flat panel, and that uses a lot of electrical engineering that I'm not super familiar with to convert the heat to the electricity. But then there's also flat solar panels that are solar concentrators, and those concentrators, they reflect the light. We're not using a PV system, we're using more of a collector system. The PV systems we are more mechanical engineers, the PV is more electrical engineering, and then the flat panels, just reflecting, is less efficient than a Fresnel lens.
It was a requirement of the project.
Yeah.
That's the simple answer, is from a mechanical engineering perspective, this was more in line with the skill set that they have been learning throughout the process. So, so that's the short answer. On the long answer.
On an acreage basis, they use less acreage. These kind of systems, so there's a benefit to the desert tortoises and all those other guys. If you go the non-double E route, if you go the ME route.
Right, and that brings up another point, is in a lot of these locations that don't have electricity, you get a lot of desert areas, places where it gets very hot. And how would that reduce the efficiency of your engine? Because you're going to have air that's heating up the entire engine, so the air that's trying to cool is now not going to get as cool as in different environments.
Yeah, I understand that is a concern. However, for the scope of our project, we are building and testing in Prescott. As I mentioned at the beginning, this is more of a research and development project. We're not planning on taking this system and putting it into a desert right now. That would require more research and development that lies outside our scope.
And solar panels have the same problem. There's companies in Phoenix that are ticked off because their panels on the roofs don't do well at 145 degrees. It's the same problem.
Ryan would like to articulate that a little bit more.
Just hypothesizing on the situation you're proposing here. Say if we were in the desert, you have all this acreage to work with, you could use, say, a heliostat to work, or to heat a working fluid that they could surround that hot cylinder head so you could gain much higher temperatures. Even though you're experiencing higher ambient temperatures, you could still operate it theoretically with the same efficiencies. But again, this is outside of the scope of our project.
Okay.
Well done.